All right, everybody. This one is a little bit more of a challenging problem. So we're going to determine the period of oscillations of a pendulum as a function of the amplitude of the oscillations. So we're going to begin with conservation of energy. We can express the energy of a pendulum as follows. Got the kinetic energy component, 1/2 mL squared phi dot squared. And we're going to add to it the potential energy as a function of phi. Now we're going to solve for phi, starting by solving for phi squared. This is just rearranging terms as needed. So we subtract u to the other side and divide by the coefficients. All right. Next, we're going to do some silly differential algebra by writing phi dot as dt squared over t phi squared, just taking the reciprocal of both sides. And now we're going to solve for t by multiplying d phi squared to the other side, taking the square root, and then integrating with respect to both sides. So on the left, the integral of dt is just t, and on the right, the integral is this expression. Now, to actually determine the period, capital T, we're going to take this integral and evaluate it over a specific interval of phi. So we're going from phi1 to phi2, and we're taking 2 times that interval. So in this case, phi1 and phi2 are the leftmost and rightmost positions of the pendulum as it swings back and forth. Now I'm going to draw a quick picture of the pendulum and show where these angles are specifically. Now we can express the energy in terms of the maximum position that the pendulum is able to reach, and we can write the potential energy in terms of phi. This will allow us to plug into our formula for the period. Next, we can pull the constants from inside of the radical within the integral out to simplify the overall expression and get an integral that's a little bit easier to manage. Next, we're going to do a substitution. Specifically, we're going to write cosine of phi is equal to 1 minus 2 sine squared of phi over 2. And this is not an integral change of variables. We're just using that trig identity to rewrite the inside of the radical. Next, we're going to do an actual substitution. So we're going to let sine of z equal sine of phi over 2 divided by sine of phi max over 2. This implies that dz, or cosine z dz, is equal to 1/2 cosine phi over 2 d phi, still over sine phi max over 2. And we can start plugging in our expressions to help evaluate this integral. Now, making sure to adjust the bounds of the integral, we now have an integral from negative pi over 2 to positive pi over 2. Then sine phi max over 2 on the denominator, along with the radical in the denominator with 1 minus z sine of z squared. And we'll have 2 cosine z times sine of phi max over 2 on the numerator divided by cosine of phi over 2 d phi dz. Now, a few things will cancel out. So we're left with root L over G times the integral 2 times the integral from negative pi over 2 to pi over 2 of 1 over square root of 1 minus sine squared phi max over 2 times sine of z squared. And this comes from converting cosine of phi over 2 back into the variable z. Now we can write this due to symmetry as having a 4 instead of a 2. And we can create function capital K of sine of phi max over 2 that is defined as follows. The integral from 0 to pi over 2, 1 over the square root, 1 minus k squared sine squared z dz. This is a well-known type of integral, and so we can expand it in powers of k in order to further approximate our solution. But there is no closed form expression.